Sam Smith and some others.
Fantastic.
So like find me if you want to coordinate.
And I guess more housekeeping, we have talks in the morning, a couple talks in the afternoon, and poster session in the late afternoon. That'll, I think, will be upstairs. So stick around for that. Email me if you have any questions. And our first talk of the day is Ben, who's going to talk about AI ecosystem, structure, strategy, and regulation.
Hi, everybody. Can you hear me well? OK. Yeah, I'm Ben Laufer. I'm super excited to be here. I'm also excited by this karaoke news. I'll be talking about some of my work on AI ecosystems. And this is joint work with John Kleinberg, Hoda Haydari, and Hamida Oderin-Wale, all great collaborators. OK, so the topic of this workshop is agency and collaborative learning. And I think the place I want to start is just driving this intuition that, AI and machine learning technologies are possibly used across a very wide variety of contexts. These are not sort of standalone artifacts, but instead represent a sort of large-scale collaborative process with many different actors and agents. And within a particular domain, it seems that some uses make sense and others don't make so much sense. And the kind of viability of particular use of a technology depends on the surrounding market. And the other thing that I want to say that's sort of interesting about this is even though there are a wide swath of possible uses for AI technologies, all of these uses might actually be building on a lot of the same infrastructure. So there might be the same underlying model underneath these different use cases. And this connects to an idea that comes from growth economics, and the idea is general purpose technology, a technology that's potentially useful across a variety of sectors. And just to sort of drive this topic intuition further, in 2024, OpenAI announced that there would be what they called a GPT store, where people could build apps on top of GPT. And Sam Altman is quoted as saying, revenue sharing is important to us. We're going to pay people who build the most useful and most used GPTs a portion of our revenue. Now, this still hasn't exactly happened yet, but as of the end of this past year, OpenAI introduced a new version of this idea, which they called apps you can chat with. So maybe an app will pop up in the chat interface, and you can sort of interface with that app. And they also released what Apps SDK, so trying to empower developers to build on top of GPT. And so the goal that I want to put forward for this talk today is understanding what I'm calling AI ecosystems. This is this is sort of, I define AI ecosystems as networks of interacting actors and developers and fine-tuners who collectively produce AI technologies. And the roadmap will roughly be modeling AI application development and safety regulation, and then some empirical work on AI genealogies. OK, so I'm going to start by setting up some of the basic ingredients to arrive at a theoretical model to understand some of the dynamics around AI ecosystems. And so we can sort of put forward some basic parts and ingredients here, and we can see that there's already some interesting threads to pull. So we can imagine that there's a generalist who develops some capabilities that can be used across domains. The generalist creates some general technology. And then one or more domain specialists adapt it to their particular domain. And we can imagine that these different entities have different capabilities. So maybe the generalist has access to compute and engineering talent, whereas the domain specialists have domain-specific knowledge. And already we can see some interesting incentives interacting here. So we can imagine that the specialist's interest in developing the technology depends on the generalist's level of investment. But the generalist will only invest in a technology if they're sufficiently confident that a domain specialist will pick it up and adopt it and bring it to a market. And with multiple specialists, this dynamic kind of only gets more complicated because you can imagine specialist DI's investment depends on DJ, because DJ, their strategy will influence the generalist and how much the generalist will invest. So the guiding questions I want to ask about just a simple model like this is, what determines who will adopt the technology and which domain-specific uses will prove viable? What's the distribution of payoff and effort between entities? And what are the impacts of regulation that might constrain the entity's strategies? And this third question relates to sort of splashy issues that come up in the press about when an AI system or a software system causes harm, and you had many people who contributed to that system. How do you allocate responsibility? So I'm going to get a little bit more formal here and set up a game, and we call this a fine-tuning game. And this is a Stackelberg-style game with a continuous variable alpha, which we call performance. And we can imagine that the investment in performance starts at 0, and a generalist, or G, goes first and invests to some alpha naught, some positive or non-negative alpha naught, at a cost. And D invests from alpha naught to some further alpha 1 at a cost that's now a function of both players' investment variables. Now, after these two steps occur, the technology generates a revenue that's a function of the final performance. And the players, and this leaves open the question of how the players distribute it, because there have been multiple people who have contributed to the technology. So we use a revenue sharing agreement, delta, and we say the generalist gets delta of the revenue and the domain specialist gets 1 minus delta. Okay, so in thinking about how to instantiate the utilities and functional forms so we can analyze this game, we can imagine that simply the utilities are the share of the revenue that the players get minus their costs. And one natural assumption is that when we're setting up the functional forms for cost and revenue, that cost should eventually grow faster than revenue. So maybe in an initial investment, the level of revenue that you get from sort of investing outpaces the cost. But at a very high level of performance, there's sort of some diminishing marginal returns effect, and eventually cost sort of outpaces revenue. And one sort of function form that satisfies this basic requirement is the set of quadratic costs. So the form depicted at the bottom, but we can imagine we might want to expand beyond the quadratic example to more general polynomial forms or all convex costs or something like this. Okay, so the analysis for a game like this looks like working backwards. So you can imagine that the domain specialist works out their strategy alpha 1, given every strategy that the generalist might have invested alpha naught and the revenue sharing agreement delta. And once this is solved, we can sort of pop back a step in the game and solve through backward induction. Now, this helps us until the very first step in our game, which is this bargaining step. So given the solve strategies, the players have to somehow collectively agree on a value of delta. And I'm not going to get too much into the analysis of this original paper, but one sort of intuition that I want to provide is that we observe that there are many parameter situations in which the players prefer to seed revenue rather than take all of the revenue. And I don't think this comes as so much of a surprise to this audience, but the reason for this is sort of it incentivizes effort. So if one player or the other took all revenue, you'd end up with a less performant technology because the other player has no reason to invest anything in the technology. And so we see many instances of this revenue sharing agreement of the sort that Sam Altman was sort of alluding to maybe in the quote that I provided at the beginning of the talk. Okay, so this sort of was an initial paper from a few years ago, but I want to point to a broader set of papers that are sort of generally taking this game-theoretic and market-theoretic approach to understanding AI supply chains. Some of the papers And foundational work in this area comes from people in this room, including Sarah Sen and Meena Jagadisan, who have done great work on trying to understand and model these AI ecosystems. And I'm going to talk about a sort of follow-on work now that's inspired by what I'm calling the regulators problem. So I'm moving from this initial game to talk about something that we did with that game. And here I've put three different information from three different regulations on this slide: the Colorado AI Act, the EU AI Act, and the California SB 1047. Two of the three have passed into law, and one was vetoed, so it will not become law. But, and you don't need to read all of it, but the sort of point that I want to make is that each of these bills distinguish in some way between different actors involved in the AI development process. They use different names, but maybe there's like a developer and a deployer, or a upstream and downstream entity. And there are different requirements attached to these different actors. And so the regulators problem is, who should AI safety regulation target? Should it be targeted upstream at the generalist, downstream at the domain specialist, maybe at some combination of both, or maybe at neither? And so now I'm going to show how we adopted the sort of original fine-tuning games structure to try to understand the incentives at play in this regulation problem. So we can imagine that we have a game similar to the game we described before, but now there's a regulator, so there's one more player. And the regulator can target the generalist or the domain specialist. We can imagine that the technology is now described using multiple attributes, not just one attribute. And the regulator announces a regulatory floor for one of these attributes. So maybe these attributes are performance and safety, and there's some minimum floor that's required in investing along the safety attribute. And in particular, we'd like to describe cases where attributes are either complementary, meaning investing in one makes investing in the other cheaper, or intention, meaning investing in one makes investing in the other more expensive. And so we can sort of go back to the modeling step and say, let's add an additional step where there's a regulator who announces theta G and theta D, a sort of minimum threshold or requirement aimed at the generalist and the domain specialist. And the game proceeds as before, but the players are coming up with a strategy profile along multiple attributes, and they have to meet this regulatory floor. So they're constrained in some way. And the rest of the sort of function forms and cost and revenue considerations look quite similar. So the technology is described by gamma, a vector of attributes that includes alpha and beta, where beta might be safety and alpha is same as before. The technology brings in revenue, and each of the players invest along some cost, and they engage in revenue sharing. And when we use the quadratic function form that I sort of introduced before, one thing that's nice about a quadratic in 2 dimensions is that it's a bit more expressive than a quadratic in 1 dimension. And in particular, we're able to describe these scenarios where the investments are sort of complementary or in tension with one another. OK, so we do a bunch of analysis and stuff, but I'm going to just go through one example that I hope motivates the sort of flavor of the kind of analysis we do in the paper. And then I'm going to sort of discuss at a higher level what the takeaways are. So let's look at one instance of this game. So I've just chosen a set of cost and revenue functions. So this doesn't stand in for the real world, but it's just a worked example of the game. In this game, there are 3 specialists. Each specialist has a different set of costs, meaning that each specialist prefers a different combination of performance and safety. And indeed, they each end up with a different level of performance and safety from one another. And this is what I've plotted here is the solved game for no regulation. So there's no requirement, there's no constraints on their strategy. And the generalist investment profile is plotted in blue, and the 3 specialists are plotted in green. And the generalist has to choose a sort of direction that satisfies all of the 3 interests of the domain specialists, so somehow averages between them in some way. And after the generalist makes their investment, the 3 domain specialists sort of pick up where the generalist left off and pull the technology in their particular desired direction. And now we can ask, what happens if we introduce a certain regulation? This regulation takes aim only at the domain specialists. And one thing to notice about this particular regulation is that the level of safety required is below the safety that all of the specialists reach absent any regulation. So you might think, okay, everything is already met in the no regulation scenario. This regulation shouldn't affect the outcome of the game. But that is the wrong intuition. So when we solve the game in this case, what we see is that the strategies change considerably. And they change in a way that the generalist drops their investment in safety because the generalist knows that the domain specialists have to meet a minimum regulatory requirement. And so as a sort of cost-cutting strategy, the generalists can drop their safety investment. And they know that even if the technology reaches a slightly lower level of safety, the cost cutting was worth it, and the specialists have to make up most of the safety investment. Okay, and we call this phenomenon backfiring. So to get a little bit more formal, we can say a fine-tuning game exhibits backfiring if and only if there exist regulatory safety thresholds for which the game yields lower safety than it would in the absence of regulation. And we can give a general characterization. So consider the set of all quadratic cost fine-tuning games. If the players invest some non-zero amounts in both attributes, meaning for all games where the strategies yield some combination of investments, so sort of non-trivial games, then the game exhibits backfiring, or there exists some regulation that will backfire. And on the right, I've, again, just chosen a specific example of parameterized, specific parameter values. But what we can do for this example is just sweep over all regulations. So all thresholds aimed at the generalist, all thresholds aimed at the specialist, and we can map where this sort of backfiring region occurs. Yes?
So are you considering specific regulation that sets the threshold? Because in your slides you mentioned 3 regulations, and they could potentially have, not that those regulations do that, but you can imagine multiple different regulations applying and setting different thresholds. What would happen in that case?
Yeah, so one advantage to maybe aiming, sorry?
You repeat the question, just repeat.
Oh, the question was what regulation could target each of the domain specialists in a bespoke manner or individually. There could be different thresholds aimed at each of the 3 domain specialists. And I portrayed an example where the same threshold is applied to all 3. Yeah, I think like what we're showing here is that backfiring can exist in a wide swath of games, but I'm quite confident it can exist in the case where there are different thresholds, because there being one is a special case of the more general game where there's different thresholds applied to everybody. But it would be interesting to analyze like how much better you can do, for example, with regulation that targets each specialist differently.
Kind of a moderate threshold and a
Yeah.
threshold.
Yeah. This result that I'm showing here, like especially this worked example on the right, is a game with just one domain specialist and one generalist, which allows us to, but it's a great point. That is one advantage to aiming regulation downstream, is that you can sort of configure it to the specific player that you're aiming at. Okay, so let's return to our single instance. So this is now going back to the example from before with 3 domain specialists. And we can imagine that the regulation has changed. So the regulator sets 2 thresholds, one aimed at the generalist and one aimed at the domain specialists. But now notice that the regulation is binding in some way, that it sits above at least some of the investment choices, safety investment choices of the players that it targets. And when we solve the strategies for this game, we see that the regulation avoids backfiring. So the players all end up with sort of safety levels that are above where they would have ended up in the absence of regulation. So this is sort of more like an intended effect of regulation. Now, there's one additional sort of unintuitive head scratcher here, which is that when we calculate the players' utilities in this case, we actually find that they're better off than they were under no regulation. So it's sort of a curious thing. Why wouldn't they just choose these strategies when they're not constrained? In the absence of regulation, all of these strategies are feasible and available to the players. Why wouldn't they just choose those strategies in the absence of regulation? I'll answer that not on this slide, but soon. First, I'll give a general characterization like I did before. So we say that a fine-tuning game exhibits mutualism if and only if some regulatory safety thresholds Pareto improve the player's utilities compared to the absence of regulation. And again, we can give this general characterization over the set of all quadratic cost games, where here, if performance and safety are sufficiently separable, which has to do with the magnitude of the cross term in the sort of quadratic cost, then there exists a regulatory regime that sort of Pareto improves both players' utilities. And as before, we can sweep over the set of regulations aimed at the generalist and domain specialist and map out, when does mutualism occur and when does backfiring occur. Okay. So now back to this head scratcher about, why didn't the players just choose these strategies in the absence of regulation? And our findings are suggesting that regulation acts as a sort of protocol design or like a way of organizing the strategy profiles of the players, and in particular that regulation and revenue sharing together unlock strategies that were not achievable from revenue sharing alone. So revenue sharing allows for a certain set of strategies, and regulation sort of changes the set of strategies in a way that that unlocks better strategies. Another way of looking at this is like there's a sort of hidden prisoner's dilemma dynamic at play here, where the players can't commit to the strategies they really want to using revenue sharing alone. Instead, they need the regulation in order to guarantee or commit to those strategies and convince each other that they're really going to follow through with them. Okay, so that was a bunch of theory, setting up a game, analyzing a game. But one thing that we became really excited about as we were working on this project was whether we can observe some of these fine-tuning dynamics empirically. And so one place to start was Hugging Face. Hugging Face is the leading host of open source AI models. And in particular, if you go on any model's page on Hugging Face, there's a whole bunch of information. There's a model card describing what the model should be used for, who the authors are, how the model performed on benchmarks. There's a whole bunch of metadata. But possibly the most interesting to us was this little thing on the bottom right, which is called a model tree. And the model tree provides links to models that are in the same family as the model you're looking at. And what that means is if the model that you're looking at is a fine-tune, you can go to the model that it fine-tuned from. And if the model you're looking at has spawned its own fine-tunes, you can click into those as well. So this suggests that there's some graph underlying Hugging Face representing all of these fine-tuning relationships between the models. And the question is, can this graph be scraped or understood? And the answer is yes. So we were able to ingest the full snapshot of around 2 million publicly available models on Hugging Face. You can imagine a network where edges represent these derivative relationships, so whether one model was a fine-tune from another, and nodes represent a model. And one surprise to us was that these are not always star graphs or broadcast graphs, meaning they were not always depth 1. So you often hear, and the way that I set up the game at the beginning of this talk, is you often hear this idea of sort of like one general purpose model, and everybody fine-tunes from that one model. But what we observe is that there are these sprawling relationships where graphs can exhibit kind of viral growth. So model B can fine-tune for model A, model C can fine-tune for model B. So you have more than one generation. And this allows us to do all sorts of interesting analysis about these lineages of derivatives. So in particular, there's a number of things we can look at. So one thing we can look at is the biggest families that exist on Hugging Face. So here I've depicted the 2,500th, 250th, 50th, and 25th largest model trees on Hugging Face. The top 10 are too big to portray on a slide, but we can plot their growth pattern over time. And we can see the sort of S-curve adoption patterns that's sort of suggestive of adoption over a broader network. And I've been really interested in this sort of temporal aspect of how this graph expands and grows over time. And that's been sort of a source of ongoing inspiration. OK, so one question we can ask about this I think interesting data set is how different are fine-tunes from their parents characteristically. So we don't just observe these graphs, but we observe a lot of data about every model. Every model is saved using a JSON string listing its attributes. So what libraries were used, what packages were used, the set of authors of the model, and so forth. And if we think of these JSON strings as encoding some like relevant traits about the model, one thing we could say is how do these traits change over these lineages? And do they get inherited or do they mutate and so forth? And one approach we could use is, for example, take the edit distance between any two model metadata strings to see how similar two models are. It's a pretty rough approach, but broadly, what we're interested in is maybe characterizing in a formal sense the family resemblance between two models so that we can answer questions like, are siblings who share the same parent more characteristically similar than two cousins or than two randomly selected models from the entire network? OK, and so we do exactly this. We end up using a TF-IDF similarity using embeddings, and then we do a cosine similarity on those for these metadata strings. We repeat the analysis for the model cards as well, but we also run the analysis for edit distance, which I just showed, and bag of words and so forth. And the first finding which is somewhat intuitive, is that models exhibit a strong family resemblance. So two models from the same family tend to be more similar in their data than two randomly selected models in the network. Not so surprising. However, one thing that is a little less intuitive is that the sort of topological distance in network is not always a good predictor of similarity. And in particular, we often find that sibling pairs are more similar to one another than parent-child pairs on average in their data. And if you had like a basic sort of genetic model of random mutation and inheritance, you might expect that a parent-child pair is a topological distance 1, and a sibling pair is a topological distance 2, because to get from one sibling to the other, you have to pop up to the parent and then back down to the sibling. And so there are two random mutations. Still, we find that the siblings tend to be more similar than parent-child pairs. So we try to sort of characterize these relationships. And even though like a biological model might suggest that this is surprising, when we look at the fine-tuning games, actually, even though like these are not direct apples-to-apples comparisons, a lot of the examples that we were playing around with the fine-tuning games created this sort of space to describe the models and characterized these sort of like downstream models as being somewhat closer to each other in the space than they were to the upstream model. Yes, Natalie.
Interesting stuff. So would a interpretation of this be that there's this external, in when you're in a family, the only thing that matters is the DNA of the people you're related to, but that what's happening when multiple people fine-tune the same model is that they're correlating with some external thing, like some new information, some new idea on Reddit,
Totally.
something like that?
Yeah, I think that's exactly right. So one explanation for why we observe siblings to be more similar than they are to the parents is not that there's like one type of organism that's just inheriting its instructions directly from its parent, but instead that there's something characteristically different about a fine-tune and a parent, and also that maybe fine-tunes tend to be published at around the same time, so any trends in what packages get used or what processes are used would suggest more similarity between the fine-tunes than between parent-child pairs. So once we start thinking about it, there's a lot of reasons why we would observe this. But the point is to sort of go out there and do a little bit of measurement. And it actually sort of confirms this like intuition that there really are some truly significant differences in capabilities between the sort of general purpose model investment or producers and the downstream domain specialists. Yes?
I just wanted to make sure I understood your similarity measurement.
Yeah.
Just wanted to make sure I understood your similarity measurement. It has nothing to do with the actual model weights or the distribution of like the next token distributions that they're.
Right. That would be great if we could do that, if we can do that.
Why can't you?
We wanted to do a very large scale measurement. So I think it would be great to, as a next step, to actually ingest the models and in some kind of evaluation space or in terms of the distribution over next tokens, characterize their similarity. The problem is, these models vary vastly in size and modality and so forth, and it would take a lot more engineering work to actually run them. Like we're literally just scraping 1.86 million metadata JSONs from the web, and the process of actually creating an environment where we can run the models and evaluate them and then have some measurement over their similarities is more work. But it would be great to do that work and have it, and I think that would probably represent a better, more direct notion of similarity. We were really interested, we think that model weights might be a much better metaphor for DNA than the metadata. Metadata, the model weights are a lot more structural. They're about the sort of physiology of the model in some sense. The problem is that there are just a different number of weights between models, and a lot of models don't publish their weights on Hugging Face. And so one thing that we did look at was there are these things called config files, which just have certain structural information, like the number of layers or the number of weights and so forth. And we've done a little bit of analysis trying to use these config files, but even these are only available for a portion of the models on Hugging Face.
I'm a little bit confused about this comment. I'm confused about the comment about the structure, because I thought that, so if you have an edge, there was potentially a fine-tuning relationship somewhere, right?
Yeah.
And fine-tuning, you don't change the topology of the network, right? So it's got the same.
Which network are you referring to?
You don't change the topology of the model.
Okay,
So
yeah,
it's
right.
got the same number of weights.
Well,
So this discussion about whether you can compare models for the weights is only for the only time you wouldn't be able to compare them is if they don't have edges
so our network.
in your topology, right? And then we maybe don't care.
So the Hugging Face platform allows a number of different derivative type relationships. One of them is fine-tuning. Another is quantization, for example. In quantization, you are changing the number of weights because you're taking usually a model that's much bigger and making it much smaller for production purposes. And so there are a lot of examples of derivatives or fine-tunes, it's not fine-tunes, but edges in our network where there are changes to the physiology of the model. And then of course there's just questions about how, even if there are the same number of layers and the same number of weights, how these change that I think would be interesting to look at. In addition to what you brought up, which is in evaluation space or in terms of distributions over next tokens, how to think about similarity in that way. One thing that we offer in this paper is like a way of sampling pairs of models. And there is this sort of like combinatorial nuance because the number of models is 2 million, but the number of pairs of models is a lot more. And so if you're trying to sample like sibling pairs or like uncle-niece pairs or whatever it is, you have to come up with specific sampling methods. And so that might help with doing a more constrained weight-specific or output-specific similarity, because you could sample and do some like statistical reasoning about how those similarities stand in for the whole population. But yeah, we don't do that. We haven't done that yet, but it would be great if we could.
Do you have a bit more of an intuition for why the sibling pairs might be more similar? Like, could it just be some generalized version of all of the siblings being tagged with, oh, this is a fine-tune of this model, or is there something else going on?
So in the raw data, there is that part of the metadata, like this is a fine-tune of this model. We've repeated the analysis with taking out those kinds of like obvious things contributing to similarity, but there are other things like when the model was created at, where of course it would be closer for sibling pairs. We removed all of this and did a bunch of robustness checks. But I think Natalie was pulling the right thread about like these models are. There are different processes people use for fine-tunes. There are temporal effects and trends and sort of like almost fashion cycles to how people approach developing models and how they describe the models, all of which would contribute to these similarities. Yes?
Do you know which features in the metadata are contributing to the similarity? Like probably like top 5, apart from the temporal signals. Like.
So this is like we're just doing a very cursory, rough, let's dump all the data into a similarity metric and see what happens. I'm about to go now more into the like specific traits and how they mutate. So hopefully that will start to get in that direction. We didn't do like a top 5 most similar or least similar traits, but that seems like a cool thing to do. Yeah, okay, I'm gonna move on. Okay, so this was just for certain sampled subgraphs, siblings, parent-child pairs, so forth. But we consider every sort of like local topology or family structure of size less than or equal to 4, and every pairwise combination of models within those structures, and we come up with sampling methods and estimate, the characteristic similarities for all of these different sort of pairwise relationships, just to give a sense of, what similarity looks like in this network. Okay, so what else can we measure over fine-tunes? We measure a bunch of specific traits, so we get more specific than this general similarity. One thing we look at is the length of the model card, and we find that the model card length reduces drastically over the course of just one generation. So the length of the characteristic of the model card cuts in half characteristically. We also look at common phrases in the model card. So one common statement is, this model card was automatically generated, and another is sort of boilerplate text like, more information needed here. Both of those, the incidence of both of those increase drastically over one generation. And then finally, when we look at the number of languages that are supported by models, it reduces. So the general picture here seems to be documentation kind of falls away on Hugging Face. And then the other thing we look at is openness, or specifically the sort of terms of use that are enabled by models on Hugging Face. And the way that we sort of explore openness is by looking at the model's license. Licenses are documents that outline, what are the intended uses, what are the requirements around how you attribute credit to sort of base model provider. and models can be sort of more restrictive or more permissive. And most licenses have terms that say anyone who uses this model, must propagate forward all of the terms in this license. So you can't undo any of the terms. If you build on top of this model, you have to be at least as restrictive as this license. So one thing that we can look at is whether this actually happens. So we can say, let's try to come up with an ordering over the observed licenses that's most compatible with our graph. So if we have a directed fine-tuning graph, G, where each node is a model and each edge is a derivative relationship, we can say an ordering over a categorical feature is compatible with a fine-tune if the feature LU precedes LV in the ordering, and U comes before V in the observed graph. And so we can ask what ordering has the highest compatibility with G. And so taking, for example, the set of the top 20 licenses, we can solve for this total ordering over licenses and see, do licenses indeed evolve and mutate in the direction that they're supposed to? And it seems like the answer is no. So when we look at the licenses that tend to be at the top of these fine-tuning families, they're corporate licenses, and these licenses often have a lot of use restrictions around what you can use the license for. And the sense is that there are these well-resourced organizations that stipulate all sorts of things about the use of their models. And then as we go down the ordering, we see that things get a lot more permissive to things like Creative Commons and MIT and so forth. And so, so this is a finding that corporate licenses are often upstream from more permissive and copyleft licenses. And this suggests that there's somewhat of a behavioral or market preference for openness, and that preference might even be stronger than the preference to sort of remain in compliance with the law and the terms that are put forward by the models that developers are using. Okay, so now I'm going to just zoom out. So I hope I've given a sense of this sort of interest of mine in AI ecosystems. We've explored some fundamental behaviors in AI development where different capabilities yield differences in contributions among general purpose AI providers and downstream domain specialists. We see that some of these dynamics can be cooperative, where people publish or make available their models for others to use for any purpose. And other times there's fierce competition in this ecosystem. And we can explore different protocols for regulation and for steering these systems to impact incentives in a way that aligns the systems with social goals. Finally, I hope I've convinced everyone that computational and mathematical approaches are needed to understand these interactions and analyze them in a sort of nuanced way, and to observe sort of large-scale pathways of diffusion and evaluate interventions for these ecosystems. So thank you so much for listening. Here are all the collaborators and people who have helped me over my PhD, and thanks all, you've been a great audience.
Maybe we'll take one or two questions for us.
Any takers? I can hand it over to Hara. Cool. Thank you.